Hello there, my name's Luke O'Brien and I'm from the United Kingdom's National Nuclear Laboratory, or NNL as I might refer to it during the presentation. I'm going to introduce an electrochemical technology that we've developed for the decontamination of metal. The technology we call EASED, or electrolytically assisted surface decontamination, is being actively explored for the decommissioning of nuclear facilities. But before I talk about that, I'm going to start with a brief overview of the National Nuclear Laboratory for those who are not familiar with us. So at NNL, we've built a distinct identity as the UK's technical authority on nuclear fission. Over decades, we've helped sustain the UK's nuclear skills and operational capacity and built our reputation both as a technical commercial organisation, but also as a strategic national asset. We're government owned, but operate independently. We've close and established working relationships with a range of customers, including BEIS, EDF, the NDA, Sellafield Limited, Rolls-Royce and the MOD. The NNL operates out of 8 sites across the UK, comprising 4 world-leading laboratories in the northwest, 3 research sites around the UK and a base in Wales. The facilities that we manage and are custodians of have an operating value in the order of 1.5 billion. The NNL employs in excess of 1,200 employees, with a considerable combined experience of nuclear operation and sites. Amongst this, we have a range of scientists. We support a number of PhDs and sponsor, more broadly, wider national programs. I've included this slide just to illustrate where national nuclear laboratories operate. This is effectively at the interface between fundamental research, which is conducted in academia or in the supply chain in small to medium enterprises, and how this is translated through to application in industry. We work with both ends of the scale and bridge the development of technology such that it can be demonstrated and subsequently deployed. The NNL develops and maintains capabilities to support all aspects of nuclear programs, from continued operation of existing reactors through to management of wastes, geodisposal, management of nuclear materials, support to naval propulsion programs, advanced nuclear reactor and reactor cycles, space energy and security and non-proliferation. With respect to this conference and decommissioning in particular, we support a range of activities ranging from planning and characterization to prepare for decommissioning, provision of access capability to reach and deploy into difficult to reach environments, treatment technologies and approaches to manage the wastes and facilities that we encounter, and also disposal technology for disposition of waste material. So having introduced the National Nuclear Laboratory, I'll start now talking about the challenge that we're addressing in this presentation. As you're aware, the nuclear sector faces a critical decade in which the closure of facilities and the cost associated that represent both a challenge and an opportunity. In the UK, the industrial strategy and the nuclear sector deal provides a framework to help shape the future, and a major aspect of that is cost reduction, where we're targeting substantial reductions relative to the baseline programs. One target that we're looking at with this technology is the amount of intermediate level metallic waste, which in the UK there's in excess of 25,000 cubic meters alone. This metallic waste exists in complex geometries and in a variety of locations, some of which I've illustrated in this diagram here, ranging from open tanks and vessels with large areas, cells containing cell wall linings and miscellaneous items, pipework and ducting, lead shielding, and bespoke items such as glove boxes. All of this contributes, or the activity associated with this metal contributes to dose during decommissioning and also to the waste liability. In this slide, I've tried to illustrate the opportunity that we see. The opportunity is that relative to the actual thickness of the metal that exists, the actual contamination layer is minuscule, and in many cases in the order of tens of microns. So on this scale, much less than 100th of the thickness of the actual metal. So if we can effectively remove this, we can release a lot of material away from its current waste classification. So this not only reduces the costs of the disposal of waste by orders of magnitude, say for example going from intermediate level waste down to low level waste or below, but also if it can be done in situ, so where the material exists, we can remove hotspots and activity that might be constraining other decommissioning activities and increasing their cost. So if we can remove these hotspots, we can enable more hands-on operations and reduce reliance on more expensive remote decommissioning approaches. I mentioned in an earlier slide the importance and the role of the National Nuclear Laboratory in engaging with people at the lower end of the technology readiness level, such as academia and SMEs. The technology that we're presenting here has been developed in that form in working with a SME called CTech Innovation, who are experts in electrochemical engineering. We developed EASED, which is a decontamination technology that can be deployed in situ, provides a very controllable decontamination cycle. With it being electrochemical, it only conducts decontamination whilst current is flowing. And we've specified it such that it's compatible with effluent and waste routes. So the process only really adds electrons into the system if you can pick an electrolyte that's compatible with your existing infrastructure. What happens within the process is we provide an electrode which passes a current through the electrolyte, and that results in the oxidation of the metallic surface. So here the grey spheres show the metal, and the red spheres are to illustrate contamination within the metal. And what happens is that these dissolve into the electrolyte, leaving behind a clean surface. This slide just shows a range of real metallic wastes that have been treated using the technology, providing treatment down to background levels of radiation. Here we see an item that has been recovered from a uranium processing plant. Here some pipework from active facilities, and here a coupon that had been immersed in a fuel storage facility. And this slide just illustrates the relative activity levels before in blue and after in red in each of these plots. In this plot we see the activity dropping as the metallic surface is removed, and in this instance removal only required 2.5 microns of material to be removed to get down to the levels that we saw. I mentioned earlier that the technology is compatible with waste routes. Because we've only introduced electrons into the system to achieve the decontamination, the rest of the solution can be treated via conventional methods. So here is one example where we've precipitated the metal that's been removed from the surface, and then we've converted it into a grouted waste form. Alternatives exist, such as evaporation and then immobilization in either grout or glass. Through use of the technology, we can achieve large reductions in contaminated material without generating significant secondary waste. In this slide, I've shown that for every 1,000 meters squared of waste that we treated, we would only generate 1 cubic meter of effluent. In fact, we possibly generate less. This might be a conservative estimate. So we reclassify 1,000 cubic meters of material, and when this is processed, in this instance, we've assumed chemical precipitation and immobilization in grout, we'd only generate 1.5 cubic meters of waste. In the next set of slides, I'm going to show 3 variants of the process that have been developed for in situ treatment of nuclear facilities. So as part of the solution, we've developed a range of formats to address common scenarios. I'm going to go through these in turn. In each case, I'll provide just a simple schematic just describing how the technology is configured, try and show an image of the technology in action, and some of the treated material. So in this instance, we've developed a jet. So jets may be a bit of a misnomer. It's more of passing a column of electrolyte, which is pumped past an electrode surface. Where the electrolyte contacts the metallic surface, it dissolves it. The jets in this case operate in pairs, complete your circuit. So the current passes down one column, contacts the metallic surface, travels along it and back out the other column. We use an alternating current so the pairs both do productive work. Here we see a jet contacting a metal surface in one of our test systems. This was a mock-up of a fuel dissolver vessel that we're looking to treat. And in this insert down here, we see it operating in two modes. One is a rastering mode where the jets have just panned across the surface that we're treating, and they'd go across, down and along in that order. And we also let the jets linger for longer periods to simulate the removal of hot spots, so where they've effectively gone deeper into the metal surface. So whilst the jet version was developed more for larger, more open access surfaces such as the insides of tanks and vessels, we also encounter pipe work and ducting. So for that scenario, we developed what we call eased pipe, which is a pipe crawler system with a pair of electrodes that are separated by a flexible connection. Both electrodes are powered, and the power runs down an umbilical that feeds this device down the pipework. And as these electrodes pass along the metal surface, current passes from the electrode to the surface in the same way as with the jets, and back out the other electrode, and these electrodes alternate again. As this travels down, the metal and the contamination is removed into the electrolyte again. And down here we see a piece of pipework that's been treated in this fashion. So the final example that I've got a slide for is for scenarios where liquids or the presence of large volumes of liquids aren't desirable. For example, where there are limits on moderators or there is a stipulation to keep a dry environment. In this instance, we've developed a gel formulation which allows us to apply the electrolyte onto the surface to be treated, and we place an electrode on top of the gel. In this insert here, we see a gel following treatment. So what happens is that the metal and the contamination go into the gel, which can be scraped off or removed in whichever format's most appropriate for the deployment, and then immobilized in grout. And down here we see a treated surface. We originally developed this for scenarios such as treating the inside of glove boxes or specific hotspots as opposed to doing large area treatment. So just a quick slide on the next steps for the technology. We're currently in the preparatory stages for active demonstration of the technology. So for the ease jet, we're looking at treating the inside of a fuel dissolver, which would effectively cover process vessels or cell wall liners. We're also in active preparation for doing some treatment of glove boxes or metallic waste items in old facilities. And we're also doing a demonstration for active pipe work. In parallel to all this, we're also continuing to evolve designs. So in this insert, I won't go through all the details, but we'll look at a range of other ways that the technology could be deployed. And we'd like to expand the deployment formats in collaboration with other end users. So in conclusion, the nuclear sector faces a critical decade with respect to closure of facilities and the challenge posed by the costs associated with that. But that also presents an opportunity. We can reduce the financial and technical challenges associated with this waste management by applying innovative new techniques. There's an opportunity for the sector to collaborate with others in other sectors and discover transformative technologies and connect these to address the industrial challenges. One such technology is the ease technology, where we believe that we can make substantial savings both in terms of the reducing the costs associated with decommissioning, but also the final waste volumes. I'd like to finish with some acknowledgements. We have a very strong team of technologists and engineers behind this project, both in terms of resource within the National Nuclear Laboratory, but also our collaborators, CTech Innovation. I've listed some of the people involved in the programme to date. I'd also like to thank Sellafield Limited for their support in the direction of the technology to make sure that it addresses their needs. So thank you very much for listening, and if you'd like to get in touch, please email me using the details provided below. Thanks again.
Hi again, everybody. Welcome, Luke, and thank you for joining us again. That was a really good presentation, Luke, and it gave us like a real sense of how the industry has the opportunity to develop like new innovative solutions and techniques. And you know, I really agree with what you said about you know, the opportunities to collaborate both internally and externally. And personally, I feel that's really important for the sector. So thank you very much. I'm going to kick it off with a question. There's still opportunities for questions to come in, so please keep sending your questions. But to start off with, Luke, I wondered if you could please give us a bit of an insight into how this technology is an improvement over other techniques that are currently available today.
Okay, thank you. That's a good question. There's an awful lot of decontamination technologies available to like end users, and they all have their strengths and weaknesses, I suppose. The reason why we pursued this one was relative to techniques such as chemical decontamination. It's very controllable. So chemical decontaminants usually carry on acting after you've finished. So there's the risk that you can corrode downstream plant or compromise waste forms and what have you. Whereas this technology, it's only doing the decontamination when the switch is flipped, effectively in the current passing. So that's one definite advantage to end users. The other one is it's taking reagents that maybe in themselves aren't particularly effective and adding extra energy to the system, I suppose. So nitric acid would take years, if not decades, to dissolve the metal surface, whereas we can make it happen in minutes. So it's taking existing reagents and boosting them, but without actually changing the system. And I suppose, and finally, we've managed to achieve, you can reuse the reagent, so you keep the actual effluent volumes low, which is another advantage to some end users.
Okay, fantastic. We're getting lots of questions in, so that's really brilliant. Thank you. I'm just trying to go through them. Some of them are quite technical, so I'm going to try and kind of group them in a logical way. I think what makes sense is to ask these couple of questions. I mean, I think you said in your presentation, Luke, that it's not at the commercial stage yet. I just wondered if you can give like an example of the next steps, and when do you anticipate approval for use kind of in a commercial setting?
Okay, so we're ramping up to 3 active demonstrations in different settings. So one is in some what were operational fuel dissolvers in a reprocessing facility. So that's a relatively large vessel with a pump. The major complication there is actually the deployment. So like it's like performing a very clever trick shot in the pool or something. You've got to go through narrow penetrations, travel a long way, and then deploy your device there. So we're moving towards so like preliminary design for that, and we've done lots of the upfront testing. Another deployment is for cleaning out the internals of some pipe work from part of a process plant that was linked with sort of like lots of uranium operations. And yet another one is looking at miscellaneous beta gamma waste, looking at the gel deployment, basically for removing hotspots around items, so you can either perform other operations such as size reduction without having to spread activity, or you can maybe reclassify the item back through the decontamination. So those are the 3 at the moment. But as with any technology development, we're open to other opportunities to explore other deployments they're just the 3 that are currently live.
Okay, fantastic. Thank you. And on your last example, you mentioned the application to remove hotspots in situ. And we've got a question related to that. And it says, how does this technique work? Can you explain kind of in a bit more detail how that would work in that instance, please, Luke?
So in situ, I'll try and give as comprehensive but straightforward answer as possible, because there's loads of different scenarios. If it was a hotspot in a vessel or on a liner of a cell or something, then we might select, for example, the EaseJet approach, which we saw, which in fact, I mentioned it's a misnomer. It's more like a hose, like a garden hose, kind of like flow rate rather than a pressure washer. For that kind of hotspot, we might advise on the jet system, if it's a fairly large hotspot. In other scenarios, the gel is most appropriate. And if it was a hotspot in pipe work or ducting, then we go with the pipe crawler. So in practice, each of them we have to provide an electrolyte, which is either a flowing acid or an acid incorporated in a gel. And how that works in practice depends on the deployment scenario, but we believe we've got most of the common ones covered.
Fantastic. That's really interesting. Thank you. And actually, I want to pick up on something else. With you mentioned decontamination of hotspots with the EaseJet, and we've got a question asking in which time frame, what is the size of the spot? I think in your example that can be decontaminated using that process, and in which time frame. In other words, what is the speed of the decontamination?
Yeah, I thought that might come up. Now again, the most straightforward answer, but there's tweaks on this. So you can change the rate by the amount of current that you pass. So if you've got the capability to pass more current and manage any heat associated with that, then you can basically turn the knob up a bit, for want of a better description. But for the EaseJet, we'd be looking at treating, say, a square meter in about 3 hours. For an Ease pipe, for say something like a 50 millimeter internal diameter pipe, we'd probably be doing about 10 meters in a shift, so a shift pattern of around about 8 hours. And then for the Ease gel, I mean, you can pick the electrode to whatever size you need to treat and whatever shape, so whichever was most appropriate. But say, for example, an A4 sheet or something around about, I don't know, what's that, 30 by 20-ish centimeters. You can do that in about 10 minutes. Bit setup and close-up time afterwards.
Fantastic. That's really interesting. Thank you. And there's another question also that's quite technical, and it says for 1,000 square meters of surface results, 1,000 square meters of surface results in 1.5 cubic meters of waste. Can you estimate what this might mean for the cost reduction?
Yeah. I totally understand the question. It's not, and I did think about trying to simplify that, but the problem I have is to actually truly answer that, we need to make assumptions about the waste packing density in any waste form that you put it in. So that would vary if it was a pipe work, a large vessel. So different geometries would give you a different answer. So I just went for straight square meters, and the way I came up with the 1.5 cubic meters is I've assumed we've dissolved a certain amount of metal, which is up to the threshold that can be incorporated in cement. I believe more than likely you can put more than that in, but when it comes to actually working out savings, it's sort of like geometry specific, on whether it's small, dense, thick metallic infrastructures or bigger open ones, and depending on how you can cut them up and pack them in your final waste form.
Okay.
Sorry, that's a bit of a dodge, but I did try with colleagues to sort of work out a better example, but you'd have to give lots of sub-examples.
No, that's really useful, and thank you for answering. Just as a follow-on question to this, can you tell us what percentage of materials are expected to be open for free release after the process?
So as long as they're not activated, then most, I mean, for high-grade stainless steel, which is commonly employed, you tend not to, I mean, that's selected so it hasn't corroded or won't corrode. So in practice, you tend not to get much migration of activity deep into the structure. So you only need to remove a relatively small amount. If it's milder steels and what have you, and you've got corrosion deeper in, then you have to remove more. But we tend to find that gets treated quicker by virtue of the fact that it's not very corrosion resistant. So I'd say the only items that, and maybe I should have included in this presentation, but one of the limitations of this is, yeah, the metal has to be electrically conducting. So if it's coated in paint or grease or what have you, then that does actually limit the performance. It's not a complete showstopper, but that might make it a less appropriate technology. But most that we've encountered, or all that we've encountered, we've been able to treat and get down to decent levels.
Okay, amazing, thank you. And this is a really good follow-on question now, because you've mentioned one limitation. Are there any other limitations of this technology that you see, Luke? And could you share a bit more?
Yeah, I mean, as with most decontamination, or not most, as with the majority of decontamination techniques, getting the decontamination process to where it needs to be is challenging. So if a plant's not necessarily being designed with decommissioning in mind or at the forefront, then you can find that you've got relatively narrow penetrations to get in and quite long distances to travel before you can get to that. So that is a limitation that exists for this, or physical methods or lasers and what have you. And we tended to work with our remote deployment teams to come up with solutions for that. So that's one limitation. I've mentioned if you've got fouling with something that's non-electrically conducting, then that's a limitation. So you might need to actually either pre-treat that or just say, we're not going to approach it with this technology. And then most of the others we've effectively designed out or picked in the selection of this. So people worry about, or people less familiar with the approach worry about things about electrical hazards and what have you, which we've effectively managed.
Okay, that's really interesting. We do have another question, and I'm not sure if this is an issue, but somebody's asked, once you've dissolved the radionuclides in the solution, do you have any problems with precipitation or co-precipitation?
Not, I mean, you could have, depending on which electrolyte you chose, but we've gone with nitric acid for the majority of the work that we've done. There are other acids you could go with. So no, we tend not to go anywhere near any solubility limits where we see things precipitating out again. And like I mentioned earlier, the only real limitation we've imposed on ourselves is an assumed upper limit once concentrated that we can put in the grouted form. So there's an upper limit on metals that they'll happily accommodate.
Okay, that's brilliant. Well, unfortunately, we're out of time. The next session is due to start shortly, but thank you for joining us, Luke. And I'm sure if there's any additional questions, we can pass them on to you directly after the event. And the next session we have got is discussing how safer, smarter, and on-schedule decommissioning, and it's basically about digital twins and how they're transforming decommissioning planning. So please join me there with Sam and Darren in a minute. Thank you very much, Luke.
Okay, thank you. Bye.
Cheers, bye-bye.